On August 13th, 2026, NOAA's Climate Prediction Center released a discussion document that changed the entire forecast landscape for the next 12 months with a single set of probability figures. The document placed the chance of a very strong El Niño event during fall and winter 2026 to 2027 at above 90%. Not likely, not probable, above 90%. And then came the number that stopped meteorologists across every agency worldwide. A 69% chance that the October through December season will exceed every El Niño on record going all the way back to 1950. 75 years of data, hundreds of individual events. And the current forecast says there is better than 2/3 odds that what is developing right now in the tropical Pacific Ocean will be stronger than all of them. The weather shift that is coming is not a seasonal adjustment. It is a reorganization of atmospheric circulation patterns across the entire northern hemisphere, arriving on top of an already stressed climate system at a moment when the infrastructure and ecosystems that will absorb it are already depleted from the events of the previous 2 years. What follows is the most complete, honest, and data-grounded explanation of what this means, where it will hit hardest, what the historical record says about events at this scale, and what the honest caveats are that anyone responsible needs to hold simultaneously with the alarm. Start with what El Niño actually is at the physical level, because the term gets used so casually in media coverage that its mechanics become abstracted into meaninglessness. The tropical Pacific Ocean is not a uniform body of water. It has a gradient. Normally, trade winds blow from east to west across the equatorial Pacific, dragging warm surface water westward and allowing cold, nutrient-rich water from the deep to upwell along the South American coast. The result is a Pacific Ocean where the western end near Australia and Indonesia is warm and the eastern end near Peru and Ecuador is cool. That temperature gradient drives an enormous atmospheric circulation cell called the Walker circulation, which pulls moist air upward in the west, carries it aloft eastward across the Pacific, descends it as dry air in the east, and then returns it westward near the surface as the trade winds. This circulation is the engine that drives rainfall patterns, storm tracks, and temperature distributions across the entire tropical belt and beyond. El Niño occurs when that engine stutters. A weakening of the trade winds allows the warm western Pacific water to slosh eastward, warming the central and eastern tropical Pacific. As the ocean warms, it heats the air above it, alters the location where convection and rainfall occur, and fundamentally reshapes the Walker circulation into a different configuration. That reconfigured circulation then radiates its influence outward through atmospheric waves called Rossby waves and Kelvin waves that travel poleward and reshape the jet streams over both hemispheres. The jet stream changes are what most people experience as El Niño weather because the jet stream position determines where storms track, where rain falls, and where temperatures deviate from seasonal norms. During a strong El Niño winter, the Pacific jet stream shifts southward, driving storm systems into the southern tier of the United States, while the northern states experience warmer and drier conditions. The Gulf of Mexico and the southeast receive more rainfall. The Pacific Northwest gets drier. The Southwest gets wetter. California's Sierra Nevada snowpack, which provides water for tens of millions of people through summer, can receive either record snows or devastating drought, depending on the precise character of each individual event. But the 2026 event is not shaping up to be a typical El Niño, and that distinction is critical for understanding why the August 13th discussion document produced the reaction it did within the meteorological community. The CPC's August 13th discussion puts a very strong event above 90% for fall and winter 2026 to 2027 and gives the October through December season a 69% chance of exceeding every El Niño on record back to 1950. The language very strong has a specific technical meaning in the ENSO classification system. It refers to sea surface temperature anomalies in the Niño 3.4 monitoring region of the central equatorial Pacific exceeding 1.5 degrees Celsius above the long-term average. A super El Niño goes beyond that to exceed 2 degrees Celsius. The two events that previously qualified as record setters in the modern era were 1997 to 1998 and 2015 to 2016, both of which produced catastrophic consequences across multiple continents. The current 2026 development is on an even stronger trajectory than the last super El Niño events and would be record strong if verified. The subsurface data that forecasters use to track the development of these events tells the story of what is building beneath the ocean's surface. Westerly wind events have helped develop an unusually large subsurface warm anomaly called a Kelvin wave. A Kelvin wave in this context is not a surface phenomenon. It is a massive pulse of warm water traveling eastward along the thermocline, the boundary between the warm surface layer and the cold, deep ocean, at depths between 50 and 200 meters. When this Kelvin wave reaches the eastern Pacific, it forces warm water upward into the surface layer, amplifying the sea surface temperature anomaly that is already developing. The NMME forecast for the October through December period shows a significant El Niño anomaly across the tropical and northern Pacific, classified as an eastern Pacific event, but the anomaly peak across the main ENSO region is above 4 degrees, making this an extreme level event, 4 degrees Celsius above normal. That is not a margin of error. That is a categorical shift in the thermal energy driving the atmospheric system. The mid-August objective ENSO outlook points to a sustained, exceptionally strong El Niño, with little indication of a transition away from El Niño before spring 2027. That duration component is almost as important as the intensity. A brief spike to extreme temperatures and then a rapid decay would produce a sharp but short-lived atmospheric response. A sustained extreme El Niño that persists from fall 2026 through at least spring 2027 means that the altered jet stream patterns, the shifted storm tracks, and the redistributed rainfall will have a full season or more to accumulate their effects on snowpack, soil moisture, reservoir levels, wildfire risk, and agricultural output. The weather that this event produces will not be a single exceptional month followed by a return to normal. It will be an extended period of departure from normal, arriving in most of the country during the winter months that determine spring water availability, summer wildfire risk, and the agricultural growing season that follows. El Niño tends to be strongest during the winter months, and its global impacts are typically most significant in the northern hemisphere winter. During a typical El Niño winter, the jet stream over the North Pacific Ocean tends to shift southward, bringing the storm track over the southern tier of the United States. The southward shift in the storm track also leads to drier conditions over the northern Rockies and Ohio and Tennessee valleys. For temperatures, El Niño often leads to a warmer than usual winter over the northern United States. Now take that typical pattern and scale it to extreme intensity. The southern storm track does not just shift slightly southward. It anchors into a position that funnels atmospheric rivers, the narrow bands of concentrated moisture that carry roughly 90% of the mid-latitude water vapor transport in the northern hemisphere, directly at California, Arizona, and the Gulf Coast, with a frequency and intensity that ordinary infrastructure was not designed to handle. The 1997 to 1998 El Niño provides the historical benchmark for what this means in practice, and examining that event carefully is the most honest way to set expectations for what is coming. The 1997 to 1998 event peaked with a Niño 3.4 anomaly of approximately 2.3 degrees Celsius and produced a winter that changed California's relationship with water infrastructure for a generation. Atmospheric rivers hit the state repeatedly from November through March. The Russian River flooded, roads washed out, landslides destroyed homes in the Santa Cruz Mountains. Reservoirs that had been at historic lows from the preceding drought filled to capacity and spilled over, causing downstream flooding at the same time that upstream communities were receiving the first water they had seen in years. The same event that brought devastating floods to California brought a historic drought to Australia, crop failures across Indonesia, and the worst coral bleaching event in history to the Great Barrier Reef at that point in time. In total, the 1997 to 1998 El Niño was estimated to have caused 23,000 deaths worldwide and $36 billion in economic damage. The 2015 to 2016 El Niño matched or slightly exceeded the 1997 to 1998 peak in some metrics and produced a similar set of outcomes, though the intervening 2 decades of climate change had loaded the atmospheric system with additional moisture and energy, making the same peak anomaly produce more intense precipitation events than the earlier event had. The honest reporting on this event requires holding several caveats simultaneously. Peak strength is not yet locked in. The CPC's August 13th strength outlook puts a very strong peak above 90%, but the historic threshold sits at 69% for October through December. What this means in plain terms is that the most likely outcome is an event that sets records. But there is meaningful uncertainty in exactly how far above the record it goes. The difference between an event that barely exceeds the 1997 to 1998 record and one that exceeds it by half a degree Celsius is not trivial, because the relationship between the peak anomaly and the atmospheric response is not linear. Extreme El Niños push the atmospheric response into regimes that historical data has only sampled a handful of times, which means the forecast uncertainty about the exact character of the associated weather patterns is larger than it would be for a moderate or strong event whose behavior is well documented across dozens of past occurrences. For the United States specifically, the regional breakdown of what this event is most likely to produce follows a well-established but intensity-dependent pattern. California and the Southwest enter the highest probability corridor for above-normal precipitation from fall 2026 through spring 2027. This is simultaneously the best possible news for a state that ended 2025. with reservoir levels still recovering from the preceding drought, and a serious infrastructure challenge for a state whose storm drain systems, river management infrastructure, and hillside development patterns were not designed for the frequency of atmospheric river events that a super El Niño can produce. The 2023 winter following a strong but not record, El Niño produced multiple atmospheric river events that caused billions of dollars in damages, damaged critical highway segments, including parts of Highway 1 along the Big Sur coast, and triggered landslides and burn scars left by the preceding years of wildfires. A super El Niño winter will likely produce a comparable or greater number of atmospheric river events in a compressed time frame. Stormier weather is more likely in the southern United States, with chances of both rain and snow increased during El Niño winters. High tide flooding could become a higher risk in parts of the United States, especially on the west coast. The high tide flooding dimension is the one that connects this weather event to a longer-term structural problem that the immediate weather coverage tends to omit. Sea level along the California coast has risen approximately 8 inches since 1900, with the rate of rise accelerating in recent decades. High tide flooding events that would have been statistical rarities in 1990 are now recurrent seasonal occurrences in low-lying coastal communities from San Diego to San Francisco. A super El Niño winter that brings elevated sea levels from the thermal expansion of warmer ocean water, increased storm surge from more frequent and intense Pacific storms, and higher baseline tides from the ENSO-driven sea level, anomaly will push high tide flooding well beyond what even the recent elevated normal looks like. Infrastructure along California's coast that survived the 2023 winter and the 2016 winter and the 1998 winter has 3 events of incremental sea level background behind it that it did not have when it was engineered to survive the worst case. The Northern Rockies, the Pacific Northwest, and the Great Plains face a different but equally consequential set of implications. A strong El Niño winter typically delivers warmer than normal temperatures across these regions, which reduces mountain snowpack even when total precipitation is near or above normal, because more of the precipitation falls as rain rather than snow, and what does fall as snow melts earlier in the spring. For the river systems that drain the Northern Rockies and supply irrigation water for agriculture from Montana to California through late summer, and earlier and lower snowpack translates directly into reduced late-season water availability at precisely the time when crop irrigation demands are highest. The 2015 to 2016 LE. Nino reduced snowpack across the Pacific Northwest to near-record lows despite above-normal precipitation totals in some areas, because the warm temperatures shifted the precipitation from snow to rain. The snowpack that normally acts as a slow-release reservoir through the summer effectively did not exist in many drainages that year. When an El Niño intensifies to extreme levels, its influence reaches high into the atmosphere, substantially influencing winter pressure patterns across the Pacific and North America. One of the specific atmospheric patterns that extreme El Niños tend to produce is a persistent ridge of high pressure over western Canada and Alaska, which blocks the normal progression of weather systems from west to east and can force severe cold outbreaks southward across the central and eastern United States. The simultaneous occurrence of atmospheric river flooding on the west coast and cold air outbreaks in the Midwest and East is not contradictory. It is the expected consequence of a heavily amplified jet stream pattern where extreme ridges and extreme troughs alternate across the continent. The same event that is flooding rivers in California is routing Arctic air into the Gulf states, producing the kind of multi-hazard winter that the 2021 Texas freeze demonstrated is catastrophically damaging to infrastructure that was designed for a narrower range of conditions. For Florida and the Gulf Coast, El Niño is historically beneficial in one specific and very important way. It suppresses Atlantic hurricane activity by increasing vertical wind shear in the tropical Atlantic, which disrupts the organized rotation that developing tropical systems require to intensify. The 2026 Atlantic hurricane season, which began in June in the context of an emerging El Niño, has already shown some evidence of that suppression effect, with unusually high shear environment limiting development in portions of the Atlantic that would normally be active during peak season. As the El Niño strengthens through fall, that suppression is expected to intensify, potentially ending the 2026 hurricane season early without the major landfalling storms that statistical models had initially forecast for a season beginning with warm Gulf of Mexico temperatures. For communities still recovering from previous years' storm damage, a quiet remaining hurricane season would provide badly needed breathing room. But the same winter that reduces tropical storm risk will increase the risk of significant flooding from the southerly storm track, and the infrastructure gap between the two types of water damage is substantial. The global dimension of what the August 13th forecast describes extends far beyond the continental United States, and understanding that global reach is important for anyone trying to Think about supply chain disruptions, food price impacts, or the cascading economic consequences that historically accompany extreme ENSO events. The 1997 to 1998 El Niño disrupted agricultural production across multiple continents simultaneously, driving commodity price spikes in grains, coffee, and cocoa that were felt in grocery store prices worldwide. It caused devastating droughts in parts of Africa, Asia, and Australia that resulted in crop failures, famine conditions, and economic contractions that the affected countries spent years recovering from. At extreme intensity, an ENSO event does not just shift the weather in one region. It redistributes atmospheric moisture and energy globally in ways that make some regions dramatically wetter and others dramatically drier, often in the exact inverse of what their agricultural systems require. Australia's eastern agricultural regions, which depend on the La Niña enhanced rainfall of recent years for their grain and cattle production, are facing the prospect of a significant rainfall deficit as the El Niño strengthens. Indonesia and the Philippines, which received abundant rainfall under La Niña and have calibrated their crop calendars accordingly, are already seeing the early signals of drought stress in their equatorial regions. Brazil's northeast, one of the most drought-prone and food-insecure regions of that country, historically experiences some of its worst droughts during strong El Niño years. For a global food system already stressed by geopolitical disruptions to grain supplies and the accumulated impacts of the previous years of climate volatility, a super El Niño that simultaneously stresses agricultural production in multiple breadbasket regions would arrive as a compounding shock at a moment of limited resilience. All the individual model solutions agree on the end of La Niña and a shift into an early warm phase by summer 2026. That consensus across model systems is what gives the August 13th forecast its unusually high confidence level. When models built on different physical parameterizations and different numerical approaches all converge on the same directional signal at similar magnitudes, that convergence is the strongest available evidence that the physical forcing, the ocean heat content, the Kelvin wave subsurface structure, the trade wind anomaly is strong enough and coherent enough that the forecast signal is real rather than a model artifact. The uncertainty that remains is not about whether a strong El Niño is developing. The August 13th advisory makes clear that El Niño conditions are already observed in the tropical Pacific, not merely forecast. The uncertainty is about peak intensity, the difference between very strong and record-breaking extreme, and about the precise regional distribution of the atmospheric response, which depends on the exact location and shape of the maximum sea surface temperature anomaly. Treat the forecast as a probability shift rather than a guarantee. The cost of preparing for a wet winter that turns out dry is small. The cost of being unprepared for a wet winter that turns out historic is measured in years of insurance claims. That framing from the scientific community is the most practically useful way to think about what the August 13th data means for anyone making decisions that depend on the coming winter's weather, from reservoir operators managing storage ahead of a potentially intense wet season, to utility companies pre-positioning repair crews before a storm season, to agricultural operations deciding on planting schedules and irrigation investments, to homeowners in flood-prone areas of California and Arizona, assessing whether their current flood mitigation is adequate for conditions that are coming, not conditions that might come. The weather shift that is arriving is not a hypothetical. It is already visible in the ocean temperature data. The Kelvin wave that is driving the subsurface warm anomaly is already measured, already tracked, already in transit. The sea surface temperature anomaly in the Central Pacific has already crossed the threshold that defines El Niño conditions and is continuing to strengthen. The forecast uncertainty that remains is about how much stronger it gets, not about whether it is real. For the United States, what real looks like is a winter 2026 to 2027 that will very probably rank among the most impactful weather seasons in the modern instrument record, concentrated in the west and south with high-impact storm systems, in the north with potential cold air outbreaks interspersed with anomalous warmth, and across coastal regions with elevated flood risk from storms arriving against a baseline sea level that is higher than it was during any previous El Niño event. The scale of preparation that a 90+% chance of a very strong super El Niño event demands is not the scale that normal seasonal forecasts receive. And the time remaining before the winter pattern establishes itself in earnest is measured in weeks, not months. The shift has already started. The question is only how prepared the systems in its path will be when it arrives.